Oh, hi everyone. Thanks for arriving in great numbers to learn about the. Where is my printout? Oh my goodness. Ah. Yeah, and we're back. So we're taking a look at transformations of exponential functions today, and this is where we can you take the kid gloves off and use all of the tools available to us to graph some really complex exponential functions. All right, so let's take a look at how we can do it. Recall about transformations. Oh, I wish I had the transforminator with me today. Oh, I don't have the Transforminator yet, but I'll show you the Transforminator next week. It's pretty spectacular, and it's one of the projects that they did in the other class. That if we have things like that look like this. Oh, I have no. What's happening today? If I have something like g of x, which looks like a multiplied by f of bracket k bracket x minus d bracket plus c, that my a, something that's out front multiplying the whole function, that's going to create vertical reflection if it's negative. It's going to create vertical stretch if a is bigger than 1 or bigger than negative, more negative than negative 1. If its absolute value is bigger than 1. And it's going to squish if the a is between negative 1 and 1. It's going to be a squish towards the x-axis. The K transformations, that's where we get our horizontal reflections. And we've also seen those are related with like just flipping your base, doing the reciprocal of your base with an exponential function because of the way negative exponentials work. Just looking at your quiz. The negative exponentials just flip your base. Yeah. And then D, horizontal translation, moving functions to the left or right. That's when we add or subtract from our inputs. And C, we saw that yesterday, lifting our whole exponential function up or pushing the whole exponential function down and bringing with it the asymptote. So let's take a look. If we had a function like this, g of x is equal to minus 2 f of 3 x plus 2 minus 1. Of all those translations, which ones happen first? What would be the first translations we would do to g of x, to do to f of x to get g of x? Sure. What's the a gonna do? Is that a hand up? Okay. Yeah, Ali. Yeah. So this k is going to really squeeze the function horizontally, and we can apply that transformation first. So we can do the compression first. So k equals 3, and that's a horizontal compression. All things will get 3 times closer to the y-axis. And then Oscar says we should do this A transformation as well. Oscar, A is minus 2. What's that going to do?
Within the x-axis and vertical stretch.
Yeah. Vertical reflection, sure, or reflection in the x-axis. Yeah, I just called it a vertical reflection because I use different language sometimes to say the same thing. And a vertical stretch. Times 2. Good. All right. And then what's left to do? D. So what's the value of D here? Okay, and what's that 2 going to do? Excellent. Yeah, this D is, I think of it as negative 2, Patrick, but you can think of it 2, no problem, so long as you know that's moving it left. Yeah, move the function left. Two units. Good. And then how about this last one? This number here. No one's talked about that number yet. C. What's it going to do? So C equals 1. Oh, minus 1, sorry. Move the whole function down. Good. So if you can visually imagine an exponential curve, and then we're going to reflect it in the x-axis and stretch it away from the x-axis. We're going to pull it towards the y-axis by factor 3, and then we're going to move it all to the left and down 1. You can visualize in your mind a graph of what this would look like if f of x was, say, 2 to the x, if that was the parent function for g of x. Very cool skill people have now. So this is where you're going to see your values in an exponential function. The a sits outside the function and multiplies the machinery of the function there. The c also sits outside and adds on to the value, basically just increasing all the y values by itself. And then your k hangs out up here inside the exponent, ready to multiply your inputs. The d will hang out here oftentimes inside brackets with the x, ready to subtract from that. So that's where you're going to find those numbers. If you don't have that bracketed, let's say you have something that looks like this, and you want to graph f of x equals 2 to the 2x minus 4, and there's not brackets there, here you have to be careful. Minus 4 or 4 is not d, because I need to factor the k out first. I need it to be looking more like this form up here. See, k multiplied by a bracket where d is connected to x inside the bracket. You do need to factor that k out first. So if I wanted to use transformations on something like that, I could say that's equal to 2 multiplied by 2 to the power x minus 2. And then I can clearly see that k is 2 and d is, I think of it as 2, because I flip the sign as I imagine what is d. So I'm always moving with my d instead of against my d transformation. Okay, carry on. Cool. All right. So remember this one. This is something that maybe half of you will forget and then say, I don't remember talking about that. But there's all these little details. We can't, I can't review that too many times. Oh, I'll probably review that a lot of times. So rather than doing this where I show you these in Desmos, let's take a look at what happens to the domain and range, and then we'll talk about Desmos and look at Desmos. So properties of exponential functions that affect the domain and range, there's only one, and that's going to be c. And we saw yesterday that c changes the value of that asymptote, and in so doing, changes your range of your exponential function. So the range of a transformed exponential, the domain is just x's of the reals, and it doesn't matter how I transform that function, I can always use any value of x and put that into the function. And because x can be any number. We've seen that we can do negative exponents, fractional exponents, decimally weird exponents. All of them are valid. Any value of x is fine. But the range, well, y is also real numbers. These create smooth curves. In some situations, you might have like integer values for y, like how many sheets of paper thick is the piece of paper after I fold it. You're only going to get integer values of x there because you can't have like half of a fold. I can't fold a paper over half a time and say how thick is it. It's one piece thick until it's two pieces thick, and then it's two pieces thick until it's four pieces thick. So that would still follow the exponential curve, but it would be a set of points along the curve. So that would be like x's of the integers and y's of the integers, and that would be a special case. Mathematically, real numbers are all fine. And so y's of the reals, but y is greater than c if a is bigger than 0. And then you would also have y is less than c if a is less than 0. Why do I need to qualify this with a? Well, it's just like with a parabola, where some parabolas open downwards and some parabolas open upwards. These parabolas have minimum values, and their values can be y is bigger than that. And these parabolas have maximum values, and y is always less than that. With exponentials, it's similarly. They either grow or they grow negatively when a is negative. And in the cases where a is negative, then y can be all those values below c. So let's take a look at some of these in Desmos. We talked about these transformations here, -2 for a, 3 for k, -2 for d, and -1 for c. So let's take a look at some exponential functions inside Desmos and apply those transformations and see them. 2 to the x, oops, that's 2 to the x. So here is my parent function, 2 to the x. And if I have out here, put this in brackets, and multiply by -2, that was the a transformation. Notice that when I multiply by -2, that point that used to be here at 1, like 0, 1, it maps down to 0, -2. So it stretched, we multiplied the y value by -2 when we applied that transformation. Now the domain is y is less than 0. This function will, so by applying that a transformation, a -a, I flip the domain, and it's now below the asymptote. And then if I subtract 1, now notice that the asymptote, this function is now approaching -1 from the negative side. The domain is now y is less than -1. It will never be as great as -1. It will always be slightly less. And then we also had a D transformation. So if you're typing these in Desmos, you kind of need to put brackets in here because Desmos insists on bringing that like operation down below. If I add 2 to this, notice that if I undo that, there's where the function used to be. And then when I add 2, it moved over to the left, unsurprisingly. And that shouldn't surprise us as well, because now if I input 0 for x, I have an exponent of 0 plus 2. My exponent is bigger. It's like I'm further along the curve. I've dove down by 2 doublings already. So that's why that's effectively moving the whole function over this way. Things happen earlier, in other words. And then the last change that we had was a k value of 3. So let's take a look at some of these points. Let's find the point at -3 here. See here, -3 gives us a value of -2. So that's where that is right now. If I put in a 3 here, notice I hit -2 earlier. Oh, but that's applied before I shifted over with my D. That's the problem there. That's why I'm confused. Let's remove this for a second. We should apply this K transformation first to see really what it's doing. So here is this point -3, and then we have the value -1.25. Okay, let's find where we hit y is equal to -1.25 as I apply this K transformation. So I go up here on the exponent level. Okay, it's not K, 3 there. And now instead of it being at -3, it's at -1. That point got pulled 3 times closer to the y-axis. Basically, we took -3, that x value, and divided it by 3. Now we have -1. It's 3 times closer. If you live 300 kilometers away from something and you live 100 kilometers away, you're 3 times closer. Because you'd be twice as close if you were 50. Let's keep going. All right. So we've seen those transformations and seen how they change the domain and range. Very cool. All right. So if we looked at these functions here, tell me the domain, x's of the reals for both of them. Not very surprising. But what's the range for these two exponential functions? Can you tell me the first one? What's the range for f of x? Kind of, we were just looking at it, weren't we? Almost exactly the same.
Wait, no,
range is, imagine a mountain range. It's so tall and beautiful. How tall is the mountain range? And then domain, think the lions. This is the domain of the lions. They live on a horizontal surface. No. Is not greater than -1 because of this guy. You see, this function's been reflected in the x-axis already. So we can imagine that this function here. Oh, that's very good, Miley. So there's a -1, and this one is doing something like this. Okay, that's f of x. Here is the line y is equal to -1, and that's what it's up to because it was reflected in the x-axis before. This one here, on the other hand, What's g of x up to? What does g of x look like? Yes, y is greater than 2. So here's the line, y equals 2. And this one is also growth, so it's also doing this, and it blows up because it has a really big b value. It's not really big, but 4. If I start quadrupling 4 multiple times, that grows a lot faster than doubling 2. Very, very much faster. Okay, so very good. Good, so we've got that. So here is a method that you can use to graph transformed exponential functions. You can use the method we used yesterday, which is just feed your function x values. Feed it the values -2, -1, 0, 1, 2, see what happens. But if your d is like -2000 because it's the year or something, and you want that to be like year 0, year 2000, you want that to be year 0, you might use a d transformation of -2000. Don't feed it the values -2, -1, 0, 1, 2. Feed it the values 1998, 1999, 2000, 2001, 2002, or feed it the values that are appropriate for the application you're looking at. But in this case, you can still just feed it x values and create a new table. Or use this method. This method here is what we looked at last unit, which is create a table of values for your parent function, and then apply the transformations point by point to those to create a graph of your more complex function. So let's take a look. All right, so if we want to graph this transform, oh, really? I don't have all the examples that we were going to do together? I don't have any of them. Oh, I thought I had them in this package. Let me just get that up. I'll get the same package as you in just one moment here. All right, let's keep going. So here is how I would apply this method. Let's take a look at 3 to the x minus 5 plus 8. Oh, I'm still frozen? Oh, no. So many technical difficulties. All right, there we go. So this one, what kinds of transformations are we applying? Nah, just a d and a c. Because this is part of the parent function. That's like the base of the exponent.
Wait,
Yeah.
so we're just doing -5 and 8?
Yeah, so these we're doing d is, I think of it as +5 and 8 there for c. So here's how I would do it. I would make my table of values for the parent function. In this case, the parent function is 3 to the x. So 3 to the 0 is 1. 3 to the -1 is 1 over 3. And 3 to the -2 is 1 over 9. 3 to the 1 is 3. And 3 to the 2 is 9. Oh yeah, I was going to ask you to count them in the positive and negative direction this morning, but hey, forgot. Okay, now, what are you confused about?
Well, I don't know if we do. Are we doing the other ones too?
What do you mean?
The x plus 5?
Yeah, that's the next step, Malcolm.
Oh, I'm sorry.
Yeah, but thank you for your question. I do appreciate you sharing it with us. Yes, and now I'm going to do the next thing, which is, these are translations. This is a D, and this is a C. So we're going to apply this D transformation by moving everything in the positive 5 direction on the x-axis. Add 5 to all my x values. So this would be 5 and 1/9, 5 and 1/3, 6, 8, 14. And then over here, y plus 8. Sorry, I don't understand. Sorry, I couldn't hear the last bit, Ella.
Why is it 5 and then 1 over 9?
Because I added 1/9 to 5. Oh, you're right. Ella's right. Yeah. So I take my x values and I add 5.
Yeah. I wrote it.
I'm here. I'm still here.
How?
Thank you very much, Ella. I got so excited to do this. And then we take our y values and add them to our y values here. 8 and 1/9. My goodness. 8 and 1/3, 9, 12. Oh, that's not even 12. Holy, 11. And then 17. Oh, man. Wow. Hey, Ella. Thank you for showing up for your learning today. Allie?
How did you find the 1/9?
The 1/9. So I did 3 to the negative 2, which is equal to 1 over 3 to the 2, which is equal to 1 over 9.
Wait, hold on.
Must be the hat.
Mr. Jennings, how do I plot 2, 9, and 17 all in one point?
2, 9, and 17.
Malcolm, you only use these two. Only use these two.
Okay, so let's go.
Because those are the fully transformed.
So now I'm going to plot these points. So I have the point 3, 8, and 1/9. So that's there. And then I have 4, 8, and 1/3. That's there. Maybe a little lower than that. 4 and 9. Yeah, 4, 9. 5, 9. Yeah, sorry, 5, 9. 6, 11. 6, 11.
Oh, I see where you're going with this.
And then 7, 17.
Wait, how did you plot 3, 8,
Huh?
9?
There.
I
Yeah?
think it would have been a good idea to stay home today.
Oh yeah, is that bad? I'm sort of feeling that way about myself. I'm wondering why it's not a snow day. Yeah, oops. So now we've got our points. The next thing will be, we've got those points graphed. Go ahead and take a look. What's the asymptote of this function? Y equals 8. So I'm going to go down and put a little graphy line here. Just a little bit of like a dotty line to remind myself not to cross that line while I'm graphing this. And then I'm going to go ahead and join these points with a smooth curve. And it should go along being closer and closer to 8. Oh, I crossed it. Darn. Yeah, so don't cross your asymptote there. Yeah, I'm very disappointed with myself with this example. As you can see, I'm taking it really hard. All right, so that's about how hard I want you to take your math mistakes. The quicker you can find humor and say, I thought 2 to the negative 1 was negative 2 again. And then you laugh at yourself a little bit. Because that way you and I are laughing together instead of me laughing at you. Oh, that was mean, wasn't it? I didn't mean to be so mean. I thought it might come out funny. Didn't come out funny. Yeah. All right. All right, shall we take a look at another example? Okay, let's look at another example together, and then I'll give you some time with the final example. What's my parent function here for g of x?
I don't even know. Oh, it's 2. It's 2 to the x.
So we'll think about 2 to the x as my parent function. Yeah. Yeah, Malcolm?
On the test, are you going to give us this fancy table?
You can make your own fancy table, Malcolm.
Well, I don't know how to do that.
You don't know how to do that? So you start with like, it kind of looks like a hashtag, except it has more boxes. All right, so here you go, 2 to the x. So I fill in my parent function table. 2 to the 0 is 1. 2 to the 1 is 2. Let's see if I can do this without causing a whiteout shortage. 2 to the 2 is 4. And then I can also, one trick if I want to do the negative side is just take the reciprocal of the opposite side. So the reciprocal of 2 is 1/2, and the reciprocal of 4 is 1 over 2, or 1 over 4. All right. Now, what are the transformations I'm applying here? There's an a value. Oh yeah, I wanted to do this in another color, but hey, the past is the past. So there's an A value, Miley says. Miley, what's the A value that I just circled? This is studying math in 2022. What number did I just circle? That's 5. Yeah, so the A value is 5. And then what's my K value? I'm going to circle it. What's my K value?
I said 3.
Yeah, this is studying math in 2022. I ask a lot of trick questions. So my K is clearly 1/3.
I solved the next bracket.
1/3 equals K.
Then why is it 3? It looks weird.
So how do I apply that K transformation to my X values? Yeah? Well, because it's X over 3. So I multiplied X by 1/3 to get X over 3.
This next example was
But it's 3x in the table.
I understood it. I get it now.
Yeah, so how do I apply that K transformation? Lily?
1, 2, 3, 4, 5.
Yeah, I use the reciprocal of K. I divide by K to change my X values. So when I divide my X values by 1/3, that's the same as multiplying them by 1/3. All right? So I flip it. Yeah. We want to get pretty good at flipping it. Flipping the number in this unit. We've seen it so much with the negative exponents, the positive exponents, and this K is like, K to the -1, and then you multiply by K to the -1 would be one way to think about it. All right, so let's apply those transformations. -2 multiplied by 3,
It's 1, 2, 3, 4, 5.
-6, -1, -3. 0 multiplied by -3, 0. 1 goes to 3, and 2 goes to 6. I multiply them all by 3. Now I could have divided all my x's by 1/3. And that would have been insanity. Because why would I do something that complicated? Why don't I just flip and multiply? X over 1/3 is equal to 3x. Just flip and multiply. Huh? Oh, because my K value here is 1/3. I've multiplied X by 1/3 to get X over 3. So I notice that as like K is not 3, K is 1/3 because the 3 is on the bottom. But then when I understand that K value, I remember I divide all of my X values by K. But dividing by 1/3 is same as flip and multiply just by 3. Sierra?
Aren't you supposed to like multiply the 2x for the 3x twice? Or
Multiply the
is it-
2x?
Yeah, like are you supposed to do like for the
They're not
right
copying
there?
those.
And it's supposed to be 2 times 3?
2 times 3? Oh, no, because 2 here? 2 is the base number, so it's not the A transformation or the K transformation. It's related to K, but we just think about it as the parent function. So my parent function here is 2 to the x, and that's where I get the parent function is that number.
Yeah, but are you supposed to like multiply the points under 2x and get 3x points?
No, they generate the table of values for the parent function.
But then on the other one, you did 3 plus 5 equals 8. Oh, wait.
Oh, I did. I took for the other one. I did like this x value plus 5 equals 3, and that's because we have here this 5. Okay, but there the 3 to the x is what generates my table of values for the parent function. Here it's 2 to the x is my parent function, and that generates this table of values there.
So many circles.
I know, that's why I kind of circle as I talk and then erase them. Yeah. Okay. All right. Let's keep going. Then I multiply my y values by 5. So what's 1/4 multiplied by 5? Yeah, I'm going to multiply all my y values by 5 because a is 5. So 1 1/4 is good, or just write down 5/4. 5/4 is fine, or 1 1/4. Both are good. 1/2 multiplied by 5. 5/2, or that's also 2.5. You can think of that as 2.5. I'll do decimals as opposed to mixed numbers over here. Okay. 1.25. 2.5. understand it in your own way, but probably those are the easiest to put on a number line. 1 multiplied by 5? I think it's 5. 2 multiplied by 5?
10.
10. 4 multiplied by 5?
20.
20. Isn't math class lovely? Aren't you glad you came today, Malcolm?
No.
No. Just flat out. Just tell it like it is. And thanks very much for your candor. All right, here. So let's go ahead. We'll find minus 6 in the x and graph 1.25. It's about right there. Boop. And then minus 3 and then 2.25. It's there. Boop it. Yeah, I did 2.5. I think. Oh, I did? Sometimes I say things that don't match what my brain is thinking. That happens more often than you'd like to know. 0 is 5. 3 is 10, thank you. 6 is 20. Just off of my graph. My goodness, how will I ever graph it if it's off my graph? It's right there. Okay. Where's the asymptote for this function? Yeah, not quite. Almost. This one's 0 because it has no c value. So the asymptote is going to approach 0 as my x values get very large but negative. So then join all these with a smooth curve. And approach your asymptote in that direction. Okay, there you go. That's g of x. Now, you got a bit of time to graph yourself some h of x. Okay, but here's what you're going to need to do. I'll help you prepare your transformation ideas here. Notice my parent function first. 1/2 to the x. Raise those to the different powers. Psst, it's just a reflection of that table. And then, what are my transformation values? What are my a, k, c, and d here? That's right, it's parts of the alphabet. Which parts of the alphabet correspond to which numbers there? I have one of each. There's all 4 transformations here for you to graph. 7 is A, thank you, Hannah. -3 is C, good. Yeah, 3 is K. Yeah, I think of it as -6. -6 is D, K is 3, A is 7, and C is -3. So, how do I, once you've generated your table of values for the parent function, 1/2 to the x, what are the transformation points that you're going to do to your x value and your y values? Like, what is this going to look like? What's this mini equation going to look like? First, give me the mini equation that's going to affect your x values. Yeah, so you're going to have x over 3 minus 6. Of course, you're going to divide these x values by 3 first, and then take away 6. And then here, ay plus c, what is that going to look like? 7 multiplied by y minus 3. Good. And here's a tip. Maybe you're annoyed with your table, and you're like, I really wish that instead of -2 there, I had -3, because that would divide evenly by 3. You can change your table, no problem. Change this 2 to a 3 for convenience purposes, because I know all y'all prefer integers to rationals. So there you go, a little tip to help you out. Okay, so try that example on your own. And once you're done that example, you can continue checking your understanding with some textbook questions here over the weekend. And that's me. Here's my mic. Drop it. Lovely presentation, everyone. Thanks very much for your participation. And any questions, hit me up by email, Team Learn at Home. Where'd my cursor go? I really need to turn off the recording before I say something embarrassing.